Hi everyone, thanks for being here. My name is Yihan Sun, and I'm an assistant professor in the University of California, Riverside. And this tutorial will be about parallel balanced binary trees. A lot of the topics in this tutorial are based on my thesis work, and the main theme is to design simple solutions for parallel balanced binary trees with multiple useful functionalities. Okay, so what you'll see in this 1.5 hour tutorial will include algorithms and implementation details of parallel balanced binary trees. We will call the tree P-trees, standing for parallel trees. If you're interested in implementing a parallel tree yourself, this part is probably useful for you. The P-tree has been implemented in our open source parallel library called PAM. It's also available online. So I'll also mention some example codes of using the library. So if you are only interested in using the tree or using the library, you probably would be interested in this part. Finally, I'll also talk about the applications that can be solved using the algorithms and the library in this tutorial. So this part explains why we need these proposed techniques to enable so many different functionalities. So this part also gives examples to apply the tree to real-world applications. Okay, so let's start with why we need to sit here and listen to a tutorial about trees. Now we start to learn trees from our first undergraduate algorithm course, like how to do insertions, deletions, and lookups in trees, and all these algorithms are in almost every algorithm textbooks. So why we need to design new algorithms? It turns out that in the real-world applications, things are more complicated. So just insertion, deletion, and lookup algorithms are not enough, and also especially when talking about parallelism, we have more challenges. So let's look at some examples of applications. The first one is a document search engine that we use almost every day. Okay, in this example, we want to search some information related to both balanced and binary. Okay, so we can use a tree to support such a document search engine. And in this tree, it should store the information about all the documents. And some functions it should support include to construct the tree, to do some search queries or complicated search queries. And at the same time, we can add new documents to the document search engine, so we may need to update it. In practice, a very important consideration is that searching and updating can be done concurrently. When some users are calling the search queries, the server at the same time may need to add new documents to the tree. So in this case, we need both correctness and performance. The second example I want to mention is about database systems. Now in this example, we have a database storing the information of all students. Now we want to find all the young computer science students with good grades to grant them scholarship, for example. So in this case, some basic operations we'll need to consider also include the construction, search queries by student ID, or to filter all the students satisfying certain conditions. Of course, we can also update the database. The third example I want to mention is some geometric queries. Here, assume we have a lot of weather stations in, for example, California that report the local temperature, and we want to know the average temperature in the Riverside area. Okay? Or if you are familiar with the game Pokemon Go, the server would need to tell you all Pokemons around you while you are moving in the map. They are both variants of the classic 2D range query, and it can be solved by using a standard 2D range tree, so another tree structure. In its interface, we may need to construct the tree, storing all the objects. We may also need to answer some queries. For example, given a rectangle, we want to report all the points inside it. Sometimes we only need the number of points or a weighted sum. Sometimes we need to list all of them, and so on. So all of these applications are very useful and we use them almost every day. They can be supported by some tree structure, as we've seen. So designing a good tree structure will benefit many areas and applications, and exactly in this tutorial, we'll show how P-trees can help with all these applications. Okay, so P-tree is a very simple balanced binary tree. So binary simply means that each node has at most 2 children, and balanced usually aims at bounding the tree height in order of log n for a tree of size n. So on the screen, we have a wild balanced binary tree. So exactly we're interested in this. Okay, but computer scientists look at it upside down in an abstract way like this. So it's very easy to make a tree binary, but how to make a tree balanced? Balance is very important to keep the tree shallow. There are many ways to make a tree balanced. That's why we have so many different balancing schemes. The algorithm in this tutorial actually work for 4 balancing schemes, which are AVL trees, reflect trees, with balanced trees, and trees. So they are balanced with different criteria such as height, size, or depending on the power of randomness. Okay, so here I want to first let you know that the concrete definitions and balancing rules of the 4 balancing schemes do not matter in this tutorial, and I will not introduce them one by one. I totally understand if you forgot the details of them. Okay. Also, if you've never heard 1 or 2 of them, it's still okay, don't worry. We'll focus on the common properties of different balancing schemes and focus on the high-level idea. So everything in this talk or algorithm spans properties hold for all the 4 balancing schemes. Okay, so when you're following this talk, just plug in whichever you're the most familiar with. Okay, so now let's consider what do we want from a good balanced binary tree. If we go back to look at the 3 applications, we'll find out what we want. The first, all of them have very complicated queries, much more complicated than just insertion, deletion, lookup. For example, some of them need range queries, some of them need bulk updates, like to add a bunch of new documents to the document search engine, or to add all the new freshman students in this year to the student database. So the tree should be full-featured, supporting a lot of operations. Also, all of these 3 applications can deal with very big data, so we want good performance. In all of them, we need to consider parallelism, concurrency, and efficiency both in theory and in practice. Finally, with all these requirements, we don't want our solution, our tree, to be super complicated. We want an elegant solution. Can we use a generic approach to deal with different balancing schemes? And maybe even harder, can we use a generic approach for all the 3 applications and maybe more? All these are our expectation for a good tree structure, but they are not easy to achieve. The good news is that actually the magic thing we'll see in this tutorial is that P-tree can support all of this. So a P-tree would exactly look like this. Okay, and the key idea to make this possible is that all the properties are supported by a primitive for trees called join. Okay, so for functionality and performance, it's easy to understand the requirement, but what do we mean by this framework and elegance? So let's zoom in here and try to see what can we get using join. Okay, so by using join, we can design algorithms generic for different balancing schemes. So to parallelize the 4 balancing schemes, we don't need to design algorithms for each of them. Actually, we only need to design a join algorithm for each of them, and all of the other algorithms, even including insertion and deletion, can be identical across multiple balancing schemes. So we have 1 algorithm for multiple balancing schemes. And also for different applications, we can have a generic solution for different applications. We don't need to design a tree for the document searching and another tree for range queries. we can have one tree for all different problems. Okay, so the reason that we can achieve these two properties is that we use the magic primitive join. So let's first look at what is join. Okay, so the input of the join function are two balanced binary trees from the same balancing scheme, TL and TR, and an entry in the middle. We call it the pivot of the join. Okay. So this entry E should be larger than all keys in TL and smaller than all keys in TR, so it's exactly in the middle. And the return value is a new tree. It's connecting TL and TR using E in the middle. But because we want the output to be valid and balanced, so we will need to rebalance tree if necessary. So I'll also briefly describe the high-level idea of the join algorithm. Okay, so assume TL is smaller and TR is larger, the other case is symmetric. We'll first go through the left spine of TR until we find a node that is balanced with TL. Then we connect them using E and replace the original subtree. So obviously now the subtree at the red node E is balanced, and the tree maintains ordering of all keys properly. However, imbalance may occur at the parent of E, which is node 8 here. In this case, we'll need to use rotations to rebalance it, and the rebalancing algorithm will vary from different balancing schemes. I'll skip the details here, but you can find it in our SPAA 16 paper. Okay, and also in our paper we have the cost-bound proof. Okay, that's a high-level idea of join algorithm. Actually, as long as we have a correct join algorithm as a black box, we can solve the rest of the problems easily. So how does join help? By using join, we can design algorithms which are generic across balancing schemes. They're also highly parallel, they're also theoretically efficient. So actually in this tutorial, I'll not cover much about the analysis, but focus more on the algorithm and implementation. All theoretical analysis is available in our previous papers if you are interested. Then I'll talk about how to use join to enable a unified framework for multiple augmentations. And in this case, we can use different augmentations to support different applications. Finally, I'll talk about how to enable persistence using join, which makes the tree multi-versioned. This is also useful in many real-world applications. Along the way in the talk, I'll also mention some experiments and some applications. So if so far so good, we'll start with the algorithms using join. And we'll see how join can make algorithms generic across balancing schemes, highly parallel, and theoretically efficient. So we'll warm up with a simple join-based insertion algorithm. In our undergraduate algorithm courses, we've learned a lot of different insertion algorithms for different balancing schemes. So let's see what if we can make use of join. So here is the algorithm, and we have an illustration here. We want to insert this 4 into this tree here. So the base case is when the tree is empty, so we just return the tree of the single node. This is the base case. Otherwise, the input key will first be compared with the root. For example, here 4 goes left. So 4 belongs to the left subtree. In the next step, we just recursively insert 4 into the left subtree. Okay, and this is done by the recursive call. Then we have 3 parts here. The left subtree with 4 inserted into it, the root in the middle, and the original right subtree. So how can we reconnect them? Well, we can use join. Now the left subtree may be heavier with a new node inserted, but join will do all the dirty work for rebalancing as a black box and just magically get it balanced. So the insertion algorithm itself doesn't need to worry about any rebalancing issues and can even be oblivious to the balancing scheme of its own input. This algorithm can be used for any balancing scheme as long as a correct join algorithm is used. And also the cost is just order of log n, which is no more expensive than the traditional implementation. Okay, so the next two functions I want to mention are split and join to. So they are also useful helper functions in some other algorithms, so I want to talk about them here. And they're also based on join and are independent of balancing schemes. Okay, so the first algorithm I want to talk about is called split. The split is somehow the inverse of join. It takes a BST T and a key K as input, and it wants to split T into two parts. The left part, called TL, contains all keys smaller than K, and the right one, TR, contains all keys greater than K. Okay. Also, we want to return a flag B to indicate if K is found in the tree or not. Now, for example, if we have a tree like this and we want to split it by key 42, the output TL may be something look like this, TR may be something look like this, and they should both be valid and balanced. And because of 42 can be found in the input tree, the return flag B is true. Okay, so let's look at the algorithm. We can also use a recursive algorithm to deal with it. It's very similar to the insertion algorithm. So we first compare K with the root of T. We call it K prime. The easiest case is when K and K prime are equal. So we directly use the left subtree as TL, the right subtree as TR, and the flag is true. So that's the easiest case. The other two cases are just symmetric. For example, if K goes left. Now, in this case, we recursively split a left subtree of T into L and R. Then, obviously, all keys smaller than K are those in L. So TL is just L. For all the keys that are larger than K, we have three components. The right output of the recursive call, R, the root, K prime, and also all the right subtree in T are larger than K as well. So we just need to then use a join to connect the three of them, and that's TR. And that's it. This is the split algorithm. The next helper function is called join to. It is defined similar to join, but just without the middle key. It can be implemented by making use of the split function. So we can just split out the last key in TL, use it as a pivot to join the rest of TL and TR. Okay. So now with join, with split and join to in mind, let's see how we can implement other algorithms on BSTs, especially those parallel algorithms. Okay. I'll first introduce you a formula to design BST algorithms using a divide and conquer scheme. Now, first of all, if the tree is empty, we can just call some base case to deal with the easiest case. Otherwise, we have a tree. At least we have the root, the left subtree, and right subtree. So we may first do something to the root and get some result. Let's call it M. And then we can deal with the two subtrees, possibly in parallel, and get some result L and R, respectively. Finally, we can combine the results in L, R, and M. So this is to combine the results from the recursive calls and the data in the root. This sometimes can be done using a join or join to. Okay. So in this case, we can design many tree algorithms that can be work efficient, and usually this gives polylogarithmic bounds on span. Okay. So design parallel algorithms on BST is so simple, right? Let's have some practice. Now the first example is just try to design an algorithm to report the largest value in the tree. Assume the tree stores a bunch of key value pairs, and all the entries of the key value pairs are sorted by the keys. So we want to return the maximum value in the tree. It can appear anywhere in the tree. So first, the base case is when t is empty, and we can just return the smallest element. Okay, let's say it's negative infinity. And then we can recursively get the maximum elements of the two subtrees in parallel, so exactly using our formula as mentioned before. And finally, we need to combine the maximum value of the left subtree, right subtree, and the root to get the final result. So we just pick up the largest among them. So this algorithm has linear work and order of log n span, and this is very simple. This is just to get the maximum value. Actually, a more general version of this algorithm works for any map-reduce style function. Okay, so let's see how it works. Now, assume we have a tree storing a bunch of entries, and now we are given a function called map that can map each entry in the tree to a certain value. And then we're given another function called reduce that can be used to combine the values. Now the reduce function also have an identity called identity. Okay, then the same idea just applies in this case. When it's an empty tree, the base case is just to return identity. Otherwise, we first map the root to some value, we call it m. And then in parallel, we call map reduce on its left subtree and right subtree recursively. And then we combine the value of the left subtree, right subtree, and the root by the reduce function. Okay, so we call reduce on L, M, and R. And this is a result of this corresponding subtree here. Again, this takes linear work and order of log n span as long as the map and reduce function are constant cost. So this is a more general version of the get max algorithm we've seen before. So we can use it also to get, for example, the sum of all values, or the minimum of all values, or even more complicated map reduce functions. Okay, so the next example I want to mention is a filter function. Now, given a tree and the predicate f, we want to return another tree with all elements satisfying this condition f. For example, you may want to select all the values in the tree that are even, or for a tree storing students information, we want to know all the students in computer science major under 25 and so on. So again, the base case is when the tree is empty, we just return an empty tree. Then in parallel, we can filter the two subtrees respectively. Say we have output L and R. And finally, we need to decide if the root satisfies the function f. If so, the root should be included in output. So we call a join to connect L and R by the root. Otherwise, we don't need to include the root, and we just call join2 to connect L and R instead. This function also has linear work, and span is order of log n squared. So this algorithm is also work efficient and also highly parallelized. Then the next thing we may want to do is to construct the tree. When we have an array of elements, we want to construct the tree from it. Okay, and also we want this process to be in parallel. Again, we want to deal with the left and right subtrees in parallel recursively. So we have to first sort the input array. Okay, also in parallel. Next, we can just pick up the middle element as the root and build the left and the right subtrees respectively. Okay, finally we use join to connect them up. The process of build sorted, which means to construct the tree from a sorted array, actually has linear work and order of log n span, but the total cost of build on an arbitrary array is bounded by the sorting algorithm. So we can have an algorithm that is n log n work and order of log n span to build a tree from an array. Okay, So next is a function to output a tree in an array. In the output, we want to keep the in order of the tree such that the array is sorted. So this is useful when we want to print the tree or just flatten the tree. Sequentially, we can just recursively output its left subtree to an array and then write the root to the next slot and then output the right subtree from the next slot. To use the same framework to do it in parallel, the only additional thing we need to do is to take care of how we can start dealing with the right subtree before finishing the left recursive call. To do this, we can store the subtree, each subtree size in the tree node. Okay? Even though the subtree sizes are not stored at the beginning, we can use the parallel MapReduce algorithm as mentioned above to compute the size of each subtree. Okay, so this is easy. Then we have, for each tree node, we have its subtree size stored. Then since we know the left subtree size, we immediately know which slot the root entry will be written to. Okay. So all the slots to the left are for the left subtree and all those on the right are for the right subtree. So these two recursive calls can be done in parallel. In the implementation, we just introduce another parameter called offset. So this parameter denotes from which subscript of array A the entries of the current tree T will be written to. Okay, when it comes to the left recursive call, we use the same offset. When it comes to the right recursive call, we use the current offset plus the left tree size plus 1 for the root. So this algorithm also calls linear work and out of log and span. We can also use join to do range queries. Okay. Now, given the key range KL to KR, we want to output a tree containing all elements in this key range. If we look at all elements inside this range, there are some subtrees and some keys in between them. So we can just call join algorithms to connect all of them in a bottom-up manner, and this process is also equivalent to using two split algorithms on KL and KR respectively. Okay, although in implementation we don't write in this way, but conceptually this is equivalent to using two splits. So we can extract the range in order of log time to get the tree as an output without traversing all the elements in the output. So it's sublinear. If we want to flatten the result in the array, we can just call the two array algorithm we've just seen, and this needs another order of k work for output size k. So the next join-based algorithm is a bit more involved than the previous ones. It's a set operation union. And also similar idea can be applied to other set operations like intersection difference or symmetric difference and so on. So for two BSTs, T1 and T2, it will combine the two trees into another output tree T in parallel. This can be useful in scenarios where we want to combine a batch of elements to a tree. It will actually be used several times in our later applications. So the lower bound of doing this for two trees of sizes m and n, where m is no greater than n, is order of m log n over m plus 1. So this bound may look a little complicated at the first glance, so let's first try to understand it in two special cases. When the two trees are of the same size, this bound is linear. When m is much smaller than n, it is about m log n. For example, when m is 1, it is just log n. So no matter the two trees have very close or very different sizes, we want our algorithm to behave properly and to achieve optimal work. Okay, to achieve this bound. Okay, so here's our pseudocode of the join-based union algorithm. It seems very easy, right? So again, this function takes two trees T1 and T2 as input and return a tree containing the union of all elements. The first two lines are just base case. When one of them is empty, we return the other tree. And the main process looks like this. We first read the root of one tree and use it to split the other tree using the join-based split algorithm. Okay, now T1 is broken up into L1 and R1, but key 5 and T2 naturally have its left subtree and right subtree split by the root 5. So we can recursively union the two parts smaller than 5 and the two parts larger than 5, and these two unions can be done in parallel. Okay, and finally we have three parts again, and we can call join to connect the three parts together. And that's it. So this is the algorithm for union. Actually, we can implement other set operations like intersection, difference in a similar way. And sometimes we need to use join too instead of join here. Okay, the good thing for this join-based set algorithms is that they are all work efficient, meeting the lower bound I've mentioned, and they are also highly parallelized. The span is polylogarithmic. Of course, the algorithm also applies to multiple balancing schemes. As a summary of the join-based algorithms, we've seen a wide variety of algorithms using join that are work optimal and have polylogarithmic span. This tells us that join captures the intrinsic property of different balancing schemes in algorithm design. And these algorithms are also very practical. Our experiments show that they can have speed-up numbers 50 to 90 on 72 cores with hyperthreading. Okay, this is the end of part 1, algorithms using join. So in this part, we've seen join-based tree algorithms that are generic cross-balancing schemes, highly parallel, very simple, theoretically efficient, and actually they're also fast in practice. So with all the algorithms, we can now consider to extend the functionalities of P-trees. And next, we'll talk about augmentation. And augmentation can also be implemented using just join. Using augmentation, we are going to address some geometric or some range-related applications. Some examples include the weather station problem and the Pokemon Go problem, as I mentioned earlier in this tutorial. Okay, so augmented tree is not a new concept. It's a very standard solution to answering some range sum queries on trees. Assume we have a tree storing a bunch of key-value pairs sorted by the keys. Now we want to answer some queries about the sum of all the values inside the key range. Then we can augment the tree by storing in each tree node the sum of all values in its subtree, or a partial sum. Okay? Now, for example, here in the tree, we store the partial sum of all the subtrees in each tree node. Then we know that every key range can be broken up into at most order of log n relevant tree nodes and subtrees. So to answer a range sum query, we can just add this order of log n partial sums up. Okay? So to answer the range sum query, we don't need to scan all the elements inside the key range, but instead only need order of log n time. Different augmentations can do different jobs. For example, if now the queries are asking us to report the maximum value in a given key range, we can just change the augmentation to be partial maximum instead of just a partial sum and use exactly the same approach. So we can do this. And for other functionalities, sometimes we only need to change the augmentation and we can answer the corresponding queries. Okay? So we can do this for a lot of different applications. We can design and implement a lot of different trees with different augmentations in our library in hope that when the users need one, they can find it in the library. But maybe we can do better. Can we come up with a general framework for augmentations? So first, let's look at how to formally define an augmented tree. Unfortunately, before our work, there's no formal definition for augmented trees. The augmented trees is more like just an abstract concept. Here, we give a definition for a class of augmented trees, of course not all of them. So our formalization is based on key-value pairs and a map-reduce operation. Okay, we assume each tree node stores a key-value pair of key type K and value type V, and in addition, each tree node also maintains some additional information about the whole subtree. Okay, just like here, in each tree node, we also maintain the partial sum of the subtree in each tree node. We call this value the augmented value of this subtree and assume its type is A. So to compute the augmented value, we need to define two functions. A map function, which maps a key-value pair to an augmented value. For example, the augmented values in the leaves can be computed just by using this function. And in this example, G maps a key-value pair just to its value. Okay, so it extracts the value of a key-value pair. Also, we need a reduce function, let's call it F. It combines the augmented values. Now, in this example, F is just an addition. So it sums up the augmented values. We require F to be associative with an identity I. Okay, so I is also the augmented value of an empty tree. Because of the associativity, to compute the augmented value, to add everything in a subtree together, we don't need to traverse the whole subtree, but can just compute the augmented value by reading the augmented values in its two children and apply G on itself and use F to combine the three parts together. Okay, like here, we just read the augmented value 7 of the left subtree, augmented value 10 of the right subtree, and apply G on the node itself and add the three parts together. Now, interestingly, this process, the update or the recalculation of an augmented value, happens only when a node is being created or when it's involved in a rotation, so its children change. And all of these scenarios happen only in join. So to make our P-trees to support arbitrary augmentation, we only need to re-implement the join algorithm and let it use G and F to update the augmented values. All the other algorithms, the insertion, union, filter, and so on, all these algorithms, they just stay unchanged. And as long as join supports augmentation, all these functions also by default support augmentation. Okay, so we can support augmentation by just join. And also, as long as G and F are simple enough and only need constant cost, the asymptotical costs of the algorithms are not affected by augmentation also. So to implement an augmented tree or to use an augmented tree in PAM, we only need to define the keys, the values, the augmented value, and then we need to specify the two functions G and F respectively. And that's all. In fact, we can generalize this to any ordered maps. So instead of define it on a concrete data structure BST, we can define augmentation for any ordered maps or any ordered key value store. So we define the abstract data type, augmented maps, that is an extension of augmented trees. Actually, our library PAM, PAM, stands for Parallel Augmented Maps. We have a Wikipedia page, and in our papers and PAM documents, we have more information. For time limitation, I'll skip more details here, but if you are interested, you can go to the website and the documents. Okay, so by this abstraction, we can model several real-world applications just using these parameters. These include the range sum, as a running example we've been using that also works on 1D stepping query, which yields a parallel interval tree. And also it works on a 2D range query, which yields a 2D range tree. And it works for document searching also. So you don't need to read all the symbols in the table because I won't have time to talk about all the details. But the point is that to deal with all the applications using PAM, we only need to define these several parameters. Here, this 2D range query can be used to solve the weather station or the Pokemon Go problem I mentioned earlier. If you're familiar with the range tree data structure, it is a 2-level nested tree, and both levels fit in our augmented tree framework. So the augmented value of the outer tree is just another augmented tree, which are the inner trees. The reduce function f is a parallel union algorithm we've seen in the last part of algorithms. So it takes the union of the two inner augmented trees. Okay, so using PAM, implementing a parallel 2D range tree is very simple. We just define the two augmented trees by specifying these parameters, and that's it. Here as an example, this is our implementation for a parallel interval tree. To define it using PAM, we just define the key, the value, the augmented value, and more importantly, we have to define f and g. The parallel construction of such an interval tree can be done by just calling the construction function on the augmented map interface, and the stepping query can also be done by a simple function call, which is also another function on the augmented map interface. In total, it only has 53 lines of code, and we have a parallel interval tree. For many other applications, we also have around 100 lines of code. So all these applications, if you implement them from scratch, it can be thousands of lines of code even for a sequential version. As a library of trees, PAM is not specially designed for any of these applications, but can greatly simplify the implementations for them and directly provide a highly parallelized version with high performance. So I'll next show some experimental results for the 2D range query as an example. We use 100 million input points in 2 dimensions, okay, and compare with some other implementations. We didn't find comparable parallel implementations in C++, so we compare PAM with 2 well-known sequential libraries. The first one is the range tree in Seagull, and the other one is R tree in the Boost library. So they both answer the same 2D range query as our implementation does, and we run our code directly on one core for a fair comparison with the sequential libraries. Okay, so you may think that our performance may not be impressive since we introduce another level of abstraction. And also PAM is a general tree library, so it's not optimized for range queries or these geometric queries. However, our experiments show that PAM actually outperforms these existing implementations. Now this figure shows the running time, so lower is better, and the red bars are for PAM. We have construction time, query time for different query types, small or large windows, and in all cases, PAM outperformed the other 2 implementations by from 1.4 times to up to 26 times. This tells us that our implementation is fast, even running sequentially. And don't forget that PAM is a parallel library. We can achieve even better performance by using parallelism. Our implementation achieves around 60 times self-speed up on 72 cores with hyperthreading, and that shows our implementation using PAM is also highly parallelized. Some other applications along with example codes are all available in our previous papers and in the GitHub library. I'll upload the slides and the videos online later, so you can use this page as a reference if you're interested. Okay, This is a part for augmentation. We've seen the formalization of augmented trees. Its implementation can be supported by just join. We've seen how this can be used to support several applications that have simple code, parallel solutions, and are fast in practice. So our next part is about persistence using join. And especially, we'll use this property to support multi-version concurrency control on trees. So first of all, let's look at the two concepts, persistence and multi-version concurrency control, or MVCC. So what are they? Persistence is a concept for data structures. It means that a data structure can preserve its previous version of itself when being updated and always yields a new version of itself. Now, for example, if we have a persistent tree T and we insert a new element K to it, we will get a new tree T2 with K inserted, and T is not modified, so the update is not in place. We get a new version. And multi-version concurrency control, or MVCC, is a concept for database systems. When we have concurrent write and read transactions, we let the write transactions create new versions and leave the old versions behind, such that if there are any ongoing queries, they can still work on the old version. So we can clearly see a correspondence here. If we have a persistent data structure, we could make use of it to support MVCC. And next, let's think about this. Why we need persistence in MVCC? It turns out that this is an easy solution to guaranteeing correctness and efficiency for a database system. Now, first of all, queries can work on a consistent version without being affected by updates. During the execution of a long query, it will always see a consistent view of the database because the version is immutable, it cannot be modified in place. And also, writers and readers do not block each other because they work on different versions, so readers and writers can both make progress, and we can get efficiency. Here I want to use an example to help to understand why correctness and efficiency are important in practice. So this example is about a document search engine. It stores a bunch of documents, each containing a set of keywords. It answers some queries like this. So given some keywords, find all the relevant documents. Now we can have multiple concurrent queries invoked by different users at the same time. And also, the server may need to crawl new data from the internet at the same time, so new documents are added to the database. This can be done at the same time when we have queries from users. So for end user experience, it is important to guarantee that the queries are not delayed by any updates. We cannot afford queries waiting whenever a new document is inserted. Otherwise, the users may need to wait for a long time, so they can be angry. And also, queries must be done on a consistent version of the database. Otherwise, the returned result can just be wrong, so the users could also be very angry if they don't get the correct information they want. So it's very important to guarantee both correctness and efficiency. So this is not just for document databases. It is generally true for any database system with concurrent updates and queries. And this type of database systems are usually called hybrid transactional and analytical processing, or edge-type database systems. Okay, let's see how P-tree can deal with this. To make P-trees persistent, we use path copying. This means that whenever we have an update in the tree, we copy all the relevant nodes on the path. So inserting 4 into the tree T1 will get a tree T2, something look like this. And a very interesting observation is that all these scenarios or this copying also only occurs in join. So let's again use the insertion algorithm as an example to show how we can make join-based algorithms persistent. Recall that in our join-based insertion, if we want to insert 4 into the tree, we first compare it with the root 5. Okay, it goes left. Then we compare it with 3, it goes right, and reach the base case. Now we create a new node and return to the last level. Okay, now what we want to do is to join 1 and 4 using the node 3, but instead of using the old node, we copy it and use the new node as the pivot of join. Similarly, when we return to 5, again we copy it and use this new node as a pivot. And finally, we find out that we get a new tree T2 represented by the new root pointer. The input tree T1 is still there, represented by the old root pointer, and we successfully made our join-based insertion persistent. Okay, as we can see, to make the algorithm persistent, we only need to do copying in the join algorithm. Actually, not only insertion, all the other join-based algorithms can be made persistent in this way, just by re-implementing the join algorithm to copy some nodes when necessary, and the other parts in the algorithm still stay unchanged. To get a persistent union, filter, range algorithms, we don't need to modify the original join-based algorithms specially. We can just do some copies in join, and we can make all the join-based algorithms persistent. Also, the overhead caused by the copying is just a constant, so asymptotically the algorithms don't get more expensive because of copying. Finally, this process is safe for concurrency. Any number of threads can work on the tree at the same time because none of the threads will actually modify any tree node. So we have a persistent join-based algorithms using path copying, but how can we use them for multi-version concurrency control? Okay, so let's look at an example, and let's use the very typical bank account example for transactions. Now assume we have a tree, we have a P tree storing all the users of a bank and their account balance. Let's see how P tree can make sure all transactions work properly. Now assume a transaction starts. Carol transfers $2 to Wendy, and in this case, the first step we want to do is to increase Wendy's balance by $2. So this will be done by a persistent update algorithm using path copying, and we copy all nodes on the path, and we get a new version of the tree. Okay, so let's call it vtemp. At the same time, there can be multiple queries working on the database. Since we have not committed a new version, they will only see v1 and they will consistently work on this version. So everything done by the unfinished transaction is not visible to the queries. The second step of this transaction is to decrease Carol's balance by $2. This is also done by path copying, and we get a new version v2. After that, the transaction has been finished. We can commit v2. So we can do this by just swinging the new root pointer, and then the current version is now v2. So anytime you want to read the current version, you see v2, and you will see the tree rooted at Carol prime prime. Okay, so to the outside world, it looks like the two operations, the increment of Wendy's balance and the decrement of Carol's balance, become visible atomically. During this process, some working queries may have finished, some may still be working, and again, they work on their own old version without being affected by all the updates. The later queries will directly see the current version, which is v2, and they'll be working on v2 all the time. So the first benefit of using path copying is that we can achieve atomic updates in a lock-free manner. It's very intuitive and straightforward. This atomicity applies to a series of operations like this, or a bulk of operations such as taking a union. In this case, for multiple operations, we can easily make them come into effect atomically. If we want to roll back, it's also very easy. We just let the current version pointer point back to V1 again. So rolling back is also easy. Also, as mentioned, any number of concurrent operations can work at the same time without affecting each other. Finally, any operation works as if it's a single version tree. From the root pointer, the thread is only aware of the tree it works on, so no extra asymptotical cost is needed. So nice! We got a pretty good solution for MVCC in database systems for transactions. But there are still something that is not quite satisfactory. First of all, if we have two concurrent updates, they each work on a snapshot of the database. So finally, each of them gets a separate version. They don't come into effect on the same tree. The other problem is that during this process, we have created a lot of new versions, so we copied many nodes. When the node is not used anymore, we need to reclaim them, otherwise it will be a lot of space overhead. But the challenging is that by copying, different versions can share tree nodes. So when we do garbage collection, we have to be careful that we only collect the nodes that are not used in other versions. For example, after V2 is committed, vtemp is not used anymore, so those nodes that are only in vtemp should be collected. So that is just carol prem. And also, when the last query leaves V1, V1 is not used anymore, so there are two nodes that is not used in V2, though these two nodes has to be collected. So finally, only the tree nodes in V2 are left. So for the two more challenges, next I'll briefly mention our solutions to these two issues in our PAM library. So these approaches are especially suitable for p-trees, so I will briefly introduce them here. There are also, of course, the other approaches to deal with these issues in the literature. Okay, let's first look at the concurrent writes. Our solution is based on using batching to make multiple updates all apply to the same version. It means that when we have concurrent updates to a database system, we build an extra layer between the database and the users. And this batching layer will collect the concurrent updates, and once in a while, this layer commit all these updates to the database. When these updates are point updates of insertions and deletions, we can use a parallel algorithm to commit them. For example, we can use a union for all the insertions and a difference for all the deletions. Okay, so will that be an effective solution? Now, here I want to show some experimental results. We compare ptree plus batching with some existing concurrent data structures. The testing data is YCSB, the Yahoo Cloud Serving benchmark, which contains different distribution of operations to a key value store. Our experiments run on a machine with 72 cores with hyperthreading. We start with a database of 50 million key value pairs and use 10 million single operation transactions. For our batching, since we buffer the transactions for a while, we control the delay of any transaction to be within 50 milliseconds. Okay, so all the reported numbers are throughput numbers, so higher is better. We here select 3 workloads from YCSB with different read-write ratios. So in all the 3 different benchmarks, ptrees outperforms the best of the other implementations by up to 1.4 times. And if you still remember the basic idea of our union algorithm, we use divide and conquer, so at any time, 2 concurrent threads must be working on 2 different tree nodes. so we effectively avoid contention. And this is exactly the reason why P-trees with batching can outperform concurrent data structures. So our algorithm is parallel, so we will make use of multi-threads, but it avoids concurrency, so there's no contention. We analyze the performance in more details by changing the number of working threads to look at the scalability curve. We use workload A as an example where we have 50% read-only transactions and 50% update transactions. P-tree is the right curve. Now, it is not the best one when fewer threads are used because batching itself has overhead. However, P-tree has almost linear speedup, scaling up to 144 threads, and it's actually the only implementation that scales to 144 threads. This is again because P-tree does not suffer from any contention, while for all the other concurrent data structures, more threads can also mean higher contention, so the performance can even be worse when more threads are involved. Next, I'll briefly mention how PAM deals with garbage collection. We use the reference counter garbage collector, so we record how many other pointers are pointing to this tree node. Okay, in this example, node 1 and 8 have reference counter 2 because they have 2 other pointers pointing to them, and the rest of them only have reference count 1. Because multiple versions can share nodes, we have to make sure that we only collect the tree nodes that is not used by any other active versions. To collect a version, we start from the root and decrement the reference count recursively. Only when the reference count becomes 0, we collect the node. So we have a pseudocode like this. I'll use a very simple running example to show how our garbage collection algorithm works. Now we will collect T1. Okay, so we start with the root. So the current reference count is 1 for the node 5, so we can safely collect it directly. Next, we'll deal with the left and right subtrees recursively. For 3, it's the same case. The reference count is 1, so it's just collected. Then we go to the child of 3, which is node 1. The reference count is 2 for 1. So we'll just decrease its reference count to 1 and quit this process. Similarly, we also need to deal with node 8 here. And the reference count is 2. We decrease it by 1 and terminate this process. Okay, so after the garbage collection, we deleted all the nodes that are only in T1. So all the nodes in T2 are still there. Okay. So now with everything ready, let's look at how we can implement an edge type database system with MVCC. Again, edge type means we need to deal with both analytical queries and transactional updates at the same time. Let's recall the document searching problem. A standard solution for document searching is based on inverted index. For all the keywords, we keep track of a list of all the documents it appears in, so it's an inverted index. So for any searching queries, it's just finding the corresponding document list in the index for the query keywords. If we add a new document, it's very important that we add it atomically. Now, for example, if we want to add document 4, we need to add 4 to the list of all the keywords altogether atomically. Now, using P-trees, we'll implement an inverted index by a 2-level nested P-tree. So in the outer level, we have a tree as the index of words, which is the orange tree here. So the key are the words, and the values are the document lists. So every tree node will have a pointer pointing to its document list. The document list itself is another index, which is also a p-tree. So these two blue trees are the document lists for the two words parallel and tree. So they are also p-trees. If we have a searching query, we just search in the outer tree to get the corresponding inner tree. If we have a searching query, we just search the query word in the outer tree to get the corresponding inner tree. If the query is more complicated, like an AND query or an OR query, we can find the two inner trees and using our join-based union or intersection algorithms. Now, because these inner trees can be large, it's very common to have like millions of documents for a keyword. We can use our parallel union or intersection algorithm to improve the performance for queries. So at the same time, we can add new documents to the index. Then we can use a divide and conquer algorithm very similar as the union algorithm. It's also parallel. For both levels, we use path copying. And for example, now we have a document 7 containing two words parallel and tree. So we need to add D7 to the inner trees of parallel and tree. So for the two inner trees, we use path copying to add D7 to them, and in the outer tree, we also copy the corresponding paths related to parallel and tree, and let these two new tree nodes pointing to the new inner trees. And finally, we get a new root pointer, which is new version. We change the current version pointer to the new version. And what did we get? We have updated the index, adding a new document. The update is atomic. D7 will appear in the list of parallel and tree at the same time atomically. And also this update is non-destructive. If slow queries are still working on the old version is still there, it's immutable, so the queries are safe. Finally, I'll show some experimental results on an H-type database system. The data is based on the well-known TPC benchmark in the database community. We combine the TPC H benchmark, which contains many different types of analytical queries, and the TPC C benchmark, which contains many different transactions to update the database. The analytical queries and transactional updates are performed at the same time. We compare with two existing in-memory database systems, Hyper and MemSQL. So for queries, p-tree is at least 4 times than the best of the two. And for updates, we're slightly slower than MemSQL, but still comparable. And this shows that our implementation achieves good performance for both updates and queries in an H-type workload. Okay, again, using similar approach, p-trees can be used to support MVCC in many settings. This page shows some related papers. For more details, you can refer to it later if you are interested. Okay, so finally, this is the end of the part of persistence. We've seen how join can be used for multi-version concurrency control and how we can use this feature to support database systems with concurrent updates and queries. And experiments show that p-trees are also fast in practice. Okay, so finally we'll have a quick summary. In this tutorial, I've shown some useful techniques to implement parallel balanced binary trees. Now, one of the core techniques is the algorithmic primitive join. We start with designing a join algorithm for different balancing schemes, including MVL trees, red-black trees with balanced trees and trees. And then, by using the corresponding join algorithms as the black box, we can design simple and efficient tree algorithms. And next, we continue adding new functionalities to the tree, and the two main functionalities we enable are augmentation and persistence. For both of them, to support them in p-tree, the only thing we need to do is to just let the join algorithm to support them. So all the other join-based algorithms can directly use join and stay unchanged, and augmentation and persistence can be supported in this way. So in theory, we get the join-based algorithmic framework, and actually all of the join-based algorithms can be proved to achieve good bounds in both work and span. In practice, we implemented the parallel library PAM, containing all the join-based algorithms, and support both the augmentation framework and persistence. So combining theory and practice, both the algorithms and the library are simple, supporting a wide range of algorithms, and work optimal with polylogarithmic span, and they are also general for different balancing schemes. They also support abstract augmentation, and it supports persistence and multi-versioning. So this is what we call P-trees. Then using P-trees, we can design solutions for real-world applications, including interval trees, 2D range-based queries, inverted index searching, database management systems, and so on. So in summary, we get concise implementation and high performance both sequentially and in parallel. Okay, so that's all for the talk. Thanks for listening. And in the rest of the time, I'll briefly show a quick example of downloading and using the library. And if we have more time later, we can have some questions and answers. Thank you very much. To use and download our PAM library, you can go to GitHub, and under CMU Parlay, we have the repository PAM, and you can directly go into it. There is a README here, and this is how we can directly download the library, and some interface introduction, and also in the library, in addition to all the source code of the library, which is under the directory of C++, we also have some example codes for applications. For example, this under this directory, we have the code for 2D range query. Under the interval directory, we have the code for interval trees, and this is for inverted index searching. And also we have implementation for the TPCH benchmark in database systems, and so on. So there are some very brief introductions here, and if you click in each of the applications, there is a more detailed introduction here. We also have script to run the codes. Okay. So PAM also uses a PBBS library for some basic operations such as sorting and so on. There are many subroutines in PBBS that is used by PAM, so you will need to set up the submodule. Actually, you can directly use this command to download PAM, and also the corresponding PBBS library is built-in. Okay, let's look at how we can use it. Okay, so we can first download the library. Now we can see that we already downloaded the PAM library. And here are everything that we have. Okay, so to run an example code, I will use something under the directory of tests. So under tests, I'll first use the file quickexample.cpp to show an illustration of how to use the interface, how to declare a map in PAM, and so on. So let's look at how it works. So to declare a map in PAM, we first need to declare a struct of entry type. And in the entry, we first need to specify the key type and the value type. So in this case, we both of them are just integer types. So key type is predefined as an integer type. And also we need a comparison function for two keys. So this is to decide the total ordering for keys such that all the entries in the tree can be sorted by the keys. Okay. If you want to use augmentation, you also need to specify the augmented value type, which is the aug t here. Then we need the three functions related to the augmentation. getEmpty means the identity of the combine function or the reduce function. FromEntry is a map function, so given a key value pair, maps it to an augmented value. Okay, and then combine function means when you have two augmented values, you have something to combine them. You can add them, you can use max or min, and so on. This depends on your application. So in this case, we just use a max of them. So every tree node will maintain the maximum value in its subtree. Okay, if you don't want to use augmentation, the entry only needs 3 parameters, which are the key type, the value type, and the comparison function. Okay, so we design this pair type as the entry type, which is key type and the value type. Then to declare this map, you can use, if you don't want to use augmentation, it's PAM map with the entry in the template. Otherwise, if we want to use augmentation, it's augmap with this entry as the template. Okay, then in the main algorithm, let's look at what is the test. So we first generate 100 input elements from 0 to 99, and then we randomly shuffle it. The input entry keys is the value of I, which is 0 to 99, and the value is just some random things we use twice of I. Then we have 2 input arrays. The first one is the first 70 elements in the input element array, and Y is the last 40 elements. So they have, in total, they are 0 to 99, but they have overlap of 10 elements. Then we build a map from all the entries in array X, which is just to use the constructor of the map, which is PAM map here. Okay, it will be done directly by the constructor. Similarly, for Y, we also build the map from all elements in Y. And finally, we call map union to get a new map called map Z. So because our union algorithm is persistent, this map X and map Y will be combined to a new map, map Z, but map X and map Y are not destroyed, so they're still there. The update or the union is not done in place. So finally we have 3 maps, map X of size 70, map Y of size 40, and map Z should have size 100. So we check its size and check if all the elements from 0 to 99 are in the map Z, and if so, this means that our union algorithm runs properly. We also check if the tree is balanced. Finally, if everything is correct, we give a pass and a smiling face. Okay, another thing that was mentioning is that if you want to specify the balancing scheme, in PAM we support 4 different balancing schemes. You can just add another balancing scheme name here. For AVL, it's just called AVL tree and so on. And by default, it uses weight balance tree. Okay, that's it. Let's see if it can pass the test and give us a smiling face. So we first make a quick example, and directly we can run it. Okay, we get the smiling face, so it runs properly. Okay. So this is just a quick example for using union. Actually, if you look at the test parallel.cpp, there are more examples. In total, 33 different function calls and the example code of calling them. So if you're interested to use our library and you're not sure, for example, how to call the insertion algorithm, the filter, range, and so on, we have all the example codes in test parallel.cpp. So let's first make. Okay, so test parallel. If you give an argument of use, it will show you all the test IDs and the tests. And the usage is to first give the size of the first tree, the size of the second tree, The number of runs, this indicates if it's run in parallel. So we have default values for runs, and by default it runs in parallel. And test ID means which test we want to run. For example, if now we want to use the difference, okay, let's use 2 trees of 1,000 and 10,000, and call difference. Okay, we can get the running time reported. Okay, for example, now we want to test the function of range. Okay, so we will give a tree of input 1 million. Okay, and we use test range, which is 18. Okay, then we get it. Now, for example, if we want to test the union algorithm again, let's use 1 million, two sets of 1 million, and the test ID is 0. And similarly, we directly get the result and the running time here. So for all the tests, we also have example code. If you're interested, you can just read the code in test parallel. Okay. And similarly, if you want to test the applications, for example, you want to test the range query, we directly have the code, the script, and we have README for each of the applications. Okay, so thanks for listening. That's all for the part of how to download and use the library. If you're interested, you can find more information in GitHub and in my website. If you have any questions, I'll be happy to answer you now, or if later you have more questions, you can just send me an email. Okay, so thank you very much. And that's all for this tutorial. And I will be happy to take any questions.